Okay, so this is we have still three lectures including this one. And so it's going to be more hands-on. We are going to show the projects in the last one, the possible projects, and discuss them. Do a bit of recap in the next one, and that's it. So we will also have a bit of introduction in the next lecture about how medical devices of which software is classified as such are validated for to be approved for clinical use, which of course is a very interesting topic theoretically, but with ridiculously little standards by now, contrary to what you would expect. And so, first I wanted to show you what the notebook for which we started last time about classifying PET dementia images without using traditional methods. Now, this is my solution, and what I've done was, of course, this is always very important, pre-process the data to normalize them, meaning in terms of intensity. Then, of course, we just have some data display where we can see that all the data have been spatially normalized to the reference space that we introduced last time. And then what I've done, after showing you that if you do a group analysis between, at the voxel level between different subjects, is to compute the mean intensity of these three groups of subjects and show the mean intensity as compared to the healthy subjects. And you can think of this, even if you look at it as an image, you can think of it as a vector of features, highly correlated, because as you can see, given how smooth this image is, there is lots of correlation, but you can really project the patterns onto that. So what we did was to project in the algebra sense of that, matrix multiplication, the every image times the reference pattern, and if you plot it, of course here the intensity is different given the number of patients, but you can see that these features are the projection of these patterns give you some separated variables. Here I've computed the, I think this was the co-ND effect size between the subject, oh yeah, it was written, between different groups of subjects. Are you familiar with the effect size with the co-ND effect size? Maybe this is not that much used as an indicator in data science. Basically, it's the ratio between the difference of the mean times the pooled standard deviation, which tells you how separated two distributions are in terms of if you pick one single subject from one distribution or the other, how well you can recognize them. Because if you have 1,000 samples in group 1 and 1,000 samples in group B, of course you will get some statistical significance of the mean. But when you want to do classifications, you want the distribution to be separated at the individual sample level. Then the last thing, if you just plot the scatter plot, of course these patterns for which given how we define them, are not independent. So you can see that they have some correlation, but you can see that even on a 2D plot, the four groups are very well separated. Okay, and that's basically it. You can try to solve it in different ways. You can see the accuracy of classification. For some reason, in this notebook here, it's not showing the accuracy that I'm getting with a classifier, but I will check why I didn't upload the correct one. But you can get some 90% classification accuracy just working on this 3 feature. And as I said, you can work with images also in other ways, like you can work with, you can actually do a principal component analysis on the images themselves. And you can find that it's, in the field of neuroscience, it's pretty effective if you have images standardized to the standard space, and these are pretty interesting tricks. So did anyone have any specific question about this in general, or the problems of the dataset? Because now we're going to see another more advanced way to work on the same dataset. Okay, so now last time I was told that most of the students here haven't encountered the autoencoders yet, except for maybe one. So I want to give you one slide about that. This is basically a strategy for unsupervised classification and regression, in our case applied to imaging. So how is an autoencoder defined? It's the autoencoder by itself is a tool to find an efficient compression of data. So what you have is an input, X, which lies in some space of dimensionality n. Like if you have images of 512 times 512 pixels, the dimension will be, well, let's say 1024 is going to be 1 million. Then you have an encoder, which the way that I've written it, it can be anything. And it takes an input X, this input here, and it is parameterized by some vector of parameters phi. And in output, it gives you a couple of variables, and I use the meaning a couple to say that generally there will be not many. Then we have another decoder, which is another mathematical function that takes these few numbers here and gives in output something which lies in the same space of our input. So it's of dimensionality n, and it's parameterized by some other vectors of parameters. Now, where does this get interesting? So, what happens if you impose that these numbers here are few? So the dimensionality of n is much less than n. And you train, because you can train this, you have two sets of parameters to be learned, phi and theta, and you train, you maximize these parameters so that the output is as close as possible to the input. So you have a tool, a function, that given an input still produces the same input. And this per se is not super interesting. Why is this interesting? Because there is always the assumptions everywhere in the field of machine learning, in data science, even way before convolutional neural networks appeared, that there's the heuristic, which you've already seen when we were working with denoising, that natural signals can be represented in some ideal space with using very few points. This is a very powerful assumption, and it generally holds pretty well. Of course, it's an heuristic, it's not proven in general. So what you do here, generally, if you can say neural networks, convolutional, or we will always use convolutional in this course because they are the easier to implement, but any kind of neural network is a universal approximator. So it should be, it's perfect to do these two tasks here. They are perfect in general to do that. And you just train it. to get, and in this way you get the most efficient representation that you have of your data. And this means that you can, like if you have an image containing squares and circles of different sizes, you can represent it using pixels, and will take you 1 million pixels if the image is 1 million times 1 million, or just save how many circles you have and which diameter a circle has, and you can use 10 parameters. This is a massive compression. We can achieve that with natural images, but we can achieve still massive compressions. And that's pretty it. Now, the question is, what's the concept is this simple. Of course, then you can complicate it by doing some regularization on enforcing some regularity of your latent space representation. And what's the scope of doing that? Because despite the theory being this simple, the practice has really lots of application. So it's automatic feature learning. So you know that in images are full of features, but if you want to hard code a way to extract some features from an image, it's super difficult to do that. If you have your universal approximator, this convolutional neural network in this case, and you just train this autoencoder, this will do it automatically. You can use it for anomaly detection. You can represent all of your images of some normal representation, like all brains of subjects without any known pathology. Train it using only these kind of subjects, and then feed images of patients with some pathologies. If you then take the difference, what the people with the highest difference will be the one with pathologies. You can also use autoencoders for denoising. They are not the most efficient way given everything else that exists nowadays, but noise, by definition, is not something that you can compress, because noise, the only way to describe a purely random noise is really to say in every pixel what did the noise did. If you compress that, noise will not survive that. Like this also happens when you do a PCA. And actually, it has been demonstrated that, under some assumptions, of course, if you have a very shallow autoencoder, its learned transformation will be PCA, actually. And finally, the most useful thing, maybe for research applications, and not maybe for practical application, is the scope of unsupervised learning. Here we're working with dementia. Dementia doesn't have that very good gold standards. Like if you have Alzheimer's disease, I've mentioned in the last lecture how the diagnosis is super hard to perform, because you can be very sure only when you're doing an autopsy and you do a pathology study, you scan it under the microscope, slices of the brain. This, of course, comes quite too late. And most kinds of dementia have extremely unspecific symptoms. And so you don't really classify it super well. And also many kinds of dementia that you do diagnose pretty well, like Parkinson's disease, you can diagnose that. But then you find that some people will have a couple of motor symptoms and keep with the motor symptoms for a decade. Some will develop dementia in 2 years. Why? And there's no way to predict these outcomes from images. Or even with Alzheimer's disease, you have dozens of subtypes, but you cannot recognize them. So like in these gold standards, unsupervised analysis, one hopes, of course, that's never proven, that it will allow you to discover and classify the different kind of pathology subtypes. Now, questions about that? because that's everything that I have to say about the theory of autoencoders. And I want you to try, this is a more complicated task, to build on the same dementia data set an autoencoder on your own. And I've added also a CSV file to do easier handling, where you can find the age, the file name, and the sex, and the class of the subject. Class is healthy, DLB, AD, and BVFTD. And there are here lots of things to think about when you start implementing. Now, I've built on my own an autoencoder with only 32 features to describe these images, but you can feel free to experiment. Probably, given that we need to learn for classes, you might go as far as only 2 classes, or you can do anyway whatever you want. And then what you do once you have an autoencoder is to analyze the features that you have extracted in the latent space, like you can do an ANOVAs versus non-factors, you can go linear regression, you can go correlation, because you really want to do traditional methods on that. You have a very compressed set of features, and you can work directly on that. So here I have a couple of suggestions on what you need to do, things to think about. Like, do you need to split the data set in train and validations for that? Well, indeed, it's not necessary. You might do that when training the autoencoder just with a very small testing or validation data set just to see the fitting quality. But given that then you will try to do some classification in the latent space, however, the training never saw the classes. So it's you're not overfitting when you see that. Of course, an issue that you will encounter is that these are 3D values, 3D volumes, and they will require a huge amount of memory. So another challenge for you is how to handle that. The thing with nuclear medicine images is they are low resolution. You can do that on MRIs, and you find out that you can extract really lots of information from structural images, but these are not good for learning because you need much higher data spaces. So you might want to downsample them. Then also you can, these are 3D, but you're not forced to really work in 3D. I mean, you can easily work in 3D, like I'm using my computer GPU, limiting it to 8 GB of RAM, but in 3D. But you can also work in 3D using 3D data as they were multiple channels, where you can just pick, I don't know, like 4 brain slices. You don't need to use a very high number of parameters network. Indeed, we are working only with 200 images. And then there are other things you need to think of. Now, the first one should have been a question. Can you put an activation function on the bottleneck? Because if you think about it, the latent space representation should have numbers that spans the whole number. So in general, this is not really obligatory, but in general, one uses linear activation, not ReLU or sigmoids or anything. These are other things you need to keep in mind. You have a weird number of pixels, so when you start subsampling, they won't work, so you might pad or crop them. Of course, when you Then, of course, when you pass from convolutional layers to dense ones, you need to do reshaping and back. And if you're working on Colab, don't waste GPU time when prototyping the architecture of the network, of course. Do you think you have everything you need to start trying this, or any question? Any questions before trying, or we can just start and see where we're going? Okay.